Hello, welcome to Chapter 10 on oscillations, waves, and sound. In part 1 of this video lecture, we'll look at an introduction to oscillations. Chapter 10 is broken up into 3 parts. In this first part of the video, part 1, we'll look at an introduction to oscillations or vibrations and also the phenomenon called resonance. In part 2 of this lecture, we'll look at waves. We'll see an introduction to waves and also the properties of superposition and interference. And then in part 3 of this lecture, we will look at sound waves. Let's start with an introduction to oscillations. So first of all, an oscillation is a back and forth motion due to a restoring force. Oscillations are also called vibrations, or the technical term for an oscillation is simple harmonic motion. So first of all, let's think about what we're dealing with here in terms of a restoring force. The restoring force is what causes the oscillation. And a restoring force is a force that tends to return the oscillating object or system to its equilibrium position. And that's the position where there are no net forces. So let's take a look at some examples below and think about what are the restoring forces and what is the equilibrium position for each of these examples. So this is called a pendulum. A pendulum is a weight that's called a bob, and it's on a string or a rope or a cable that's attached to the ceiling, for example. And the pendulum swings back and forth. All right, we're going to study the pendulum in more detail in this chapter. Obviously, the equilibrium position of the pendulum is when it hangs straight down and is not moving at all, because when it's at rest, of course, it's at equilibrium. But if we swing the pendulum up a little bit and let it go, gravity is going to pull the pendulum back down towards the center. It's going to swing back to the other side, and then gravity is going to pull it back again. So gravity is the restoring force for the pendulum. Another type of pendulum is called a spring pendulum. And the difference here is the mass here, the block, is not swinging back and forth, but it's bouncing up and down due to the combination of the spring force and also gravity pulling down on this thing. So in this case, there are actually 2 restoring forces. The spring force and the gravitational force are making this thing bounce up and down. A tuning fork, I don't have one right with me here, but you may have seen these. Musicians can use them. You basically hit the tuning fork with a mallet, and it vibrates, and it makes sound. And in this case, the restoring force is the elastic tension in the metal here. Okay, remember that all materials have elastic properties. So this solid metal tuning fork actually sort of behaves like a spring, almost like our spring pendulum here, and that gets these little the tines of the tuning fork vibrate back and forth. We'll look at the tuning fork in more detail in a future chapter when we talk about sound. Another example of oscillations, again, having to do with sound, is any kind of instrument with strings. So, guitar, a violin, a piano, etc. When we pluck the string on the guitar, it vibrates back and forth very fast. And those vibrations are oscillations. And in this case, the restoring force is the tension in the string, right? The guitar string is pulled and stretched tight, and that tension in the string is what makes it restore back to its straight position. Oscillations are also very important when we talk about thermal properties of solids. Remember, the whole idea of thermal energy was that the atoms inside of a solid are vibrating, and so they are undergoing oscillations due to those spring-like atomic bonds attaching the atoms to one another. So in this case, the restoring force is due to the bonds that hold the atoms together. Let's now take a look at the basic properties of all oscillations. So there are 5 properties that all oscillations have in common. The first is called the period. And the period, we've seen this before, we use the letter T, the uppercase T, to designate period. That's our symbol for period. Period is how long it takes for one complete cycle of oscillation. And period is measured in seconds because it's an amount of time. Now, we have to be careful here. What this means is if this is a pendulum here, so this weight is going to swing back and forth like this on this string which is attached up here. So if we start right here and we let the pendulum swing all the way over here, well, that's only half a cycle. It has to still come back and get back to this point here. So the amount of time it takes for the pendulum to go all the way to the right and all the way back to the left is 1 period. And we could measure that, for example, with a stopwatch. The frequency is how many oscillation cycles per second there are. And so the unit for frequency is cycles per second, and a cycle per second is called a hertz, okay, which is abbreviated Hz. Now, the interesting thing about frequency and period is that they are reciprocals of one another. So if we know the period, T, we can easily calculate the frequency as 1 over T. Likewise, if we know the frequency, F, we can easily calculate the period, T. T is just equal to 1 over F. The next property that all oscillations have is their amplitude. The amplitude of oscillation is the maximum displacement from equilibrium, and it's typically measured in meters. So what this means here is, let's go back to our pendulum here, which is swinging back and forth. Well, remember the equilibrium position of the pendulum is right here where I have my pointer, because this is where, when the pendulum is hanging straight down at rest, there are no forces on, there's no net force on the pendulum. So the amplitude is defined as the distance that the pendulum moves, the maximum distance from the equilibrium position. So this displacement here from here to here is the amplitude, or we could have measured it over here from the equilibrium position to the farthest position on the right. The next property of all oscillations is that they all have a restoring force. And the restoring force, of course, is what makes the oscillator vibrate back and forth. So restoring force is a force that returns the system to its equilibrium position. We talked about several examples of this on the last slide. Just to review again, for this pendulum here, gravity makes this pendulum bob want to return and swing back down to the bottom. But then, of course, it swings past because of its momentum, carries it back up over here, and now gravity is going to pull it back to the left. So gravity is always trying to return the pendulum back to the center position, which is its equilibrium position. The last property, and we're going to look at this in a little more detail in the next several slides, is that all oscillations undergo what is called simple harmonic motion. And this is a fancy, basically mathematical term that means the position varies with time according to a sinusoidal function. It's described by either a sine function or a cosine function. And we'll look at this again in a little more detail shortly. One of the interesting characteristics of oscillations is that the frequency of oscillation is independent of the amplitude of the oscillation. And this is a little bit surprising. What it means is that if we take a pendulum and we swing it just a little bit like this, or if we swing it farther like this, it's going to have the exact same frequency. And that works for all different types of oscillation. So let's take a look at a demo where we'll look at the pendulum and the spring pendulum and explore this phenomena in a little more detail. This is a pendulum simulation tool. We'll be using it a few times in this chapter. Our goal right now is to show that the pendulum's oscillation frequency is independent of the amplitude of oscillation. So what I've done here is I've actually got two pendulums set up here. One is red, one is blue. So I'm going to take the red one and I'm going to move it over 5 degrees and let it go. And it's going to start swinging. Now I've set it to slow motion down here, which will make it a little bit easier to set up, and then I'll get it going at regular speed soon. Now I'm going to grab the blue one and I'm going to move it over 10 degrees. So it has twice as much amplitude, and I'm going to let it go right when the red one is over all the way on the right. So let me go to normal speed now, and let's watch these two pendulums swing back and forth. So you can see what's happening here is the red one is obviously moving less. It has a smaller amplitude, and the blue one is moving farther. It has an amplitude that's twice as far. However, notice that they're both moving in sync. That is, they both get to the right side and stop at the same time, and they both move to the left side and stop at the same time. Therefore, they both have the exact same period and the exact same frequency of oscillation. So this is one way of showing that the amount of amplitude does not affect the frequency of oscillation. This is another simulation tool. This one is for the spring pendulum. And a spring pendulum is when you have a mass hanging from a spring, and this mass is going to oscillate or bounce up and down. And again, our goal here in this first demonstration is to show that the amplitude of oscillation does not affect the frequency of oscillation. So in order to show this, let's get these things moving. So I'm going to take the one on the left and I'm going to give it a very small amplitude. I'm just going to pull it down a little bit and let it go and get it started. Now this one over here, I'm going to pull it down quite a bit more. And I'm going to wait till they're right at the same point and I'm going to release it. So let me go to the normal speed now and let's watch these things bounce back and forth. So you can obviously see that the spring pendulum on the left is moving a lot less. It has a very small amplitude of oscillation. The one on the right is moving quite a bit. It has a large amplitude of oscillation. However, notice that both pendulums are in sync. They are both moving up and down at the same time, and in fact they both stop at the same time, at the top and at the bottom. So they have the same exact period of oscillation. It takes the same amount of time for each one to make one complete cycle. Therefore, they also have the exact same frequency of oscillation. So this is one way to show that the frequency of oscillation is independent of the amplitude of the oscillation. Let's take a look at a little more detail now at the restoring forces that produce this so-called simple harmonic motion or back and forth motion. So our first example, imagine you have a nice round curved bowl like this, like a mixing bowl or something like that, or a cereal bowl or something. And we'll place some marble inside the bowl up here and let it go. And of course this marble is going to roll down, and then it's going to roll back up this side, and it's going to roll back and forth. Now, if there were no friction or no air resistance, this marble would actually just keep going back and forth forever, interestingly, all right? Remember, energy is conserved here, all right, as this thing goes back and forth. So in this case, the equilibrium position of the marble, you can think about where would the marble come to rest. Well, obviously it's going to come to rest at the bottom of the bowl. So here's our equilibrium position. Whenever the marble is anywhere else, notice it's gravity that's going to be pulling the marble down, and it's going to follow the track or the curved surface of the bowl. But over here, gravity is going to pull it a little bit to the right. Over here, gravity is going to pull it to the left. In all cases, gravity is going to try to restore the marble to the equilibrium position. Now, if we take our marble in the bowl and let's say we measured the distance for example, in centimeters along this bowl. And let's call the bottom here our origin. Let's call that 0 centimeters. So then over to the right, let's call that a positive distance. And as the marble, if it moves over to the left, we'll call that a negative distance. So we're going to start with the marble over here on the right side and let it go. So here's our marble. This is the position of the marble this is time here, and we're plotting position in the vertical axis here. So the marble is at this point right here. Now, as we let the marble go, notice it's going to move towards the origin, which is down here at the equilibrium position. So the marble is going to undergo some position versus time like this, and when it gets right to the bottom, the marble is right here on our graph. Now the marble, of course, swings up to the left. So on our graph, that is a negative position, and it reaches a maximum negative position right here where it stops. It turns around and it starts going back down to the bottom. So that means on our graph, it's returning back to 0 here because that's our origin. And then the marble keeps swinging up, going positive in the positive direction now, all the way to the top again. And look, we're right back to where we started from here. So this amount of time from this peak to this peak here on our graph is one period of oscillation. That's a full cycle. Remember, it started over here on the left, it went down into the, it started on the right, it went down and then to the left, and then back down and back up to the right. So this is all one cycle. And then this thing repeats, right? The cycle is going to repeat over and over. So this curve here that is plotted is the characteristic curve of a cosine function. All right, and this is one of the characteristics of simple harmonic motion. It's caused by a linear restoring force, and it results in sinusoidal motion, either a sine or a cosine function. So this is a different type of oscillator or oscillating system, which is a mass on a spring. And one way to visualize this is imagine you have a cart, maybe, or the cart could have wheels so that there's very little friction, or we could have a mass on an air track, sort of like a air hockey table, and that little cushion of air reduces friction. So this mass can slide back and forth basically without any friction. So if we pull this thing over and stretch the spring and let it go, this thing will start oscillating, just like is shown here in the little animation. And so notice the oscillation. We're going to call this, this point right here where it is relaxed. That is our equilibrium position at 0. And we're going to pull it over a distance which is equal to the amplitude of oscillation. And so it is going to swing back and forth between positive A in distance and negative A in distance. And again, A is the amplitude of oscillation. Now, if we actually plot the exact position at every little instant of time and show, so this is time going down in the graph, all right? You can see the T down here. This is the time axis moving down, and then this is distance going back and forth horizontally in this graph. But each one of these points here represents where the object is in the x-axis here at each interval of time. And so you can see if you take a lot of points here, you take about 100 data points here, notice the data points trace out a perfect sine or cosine function. So this is, again, one of the trademarks of simple harmonic motion is this sinusoidal motion that looks like a sine or cosine function. Now here's another type of mass and spring system. This one is hanging, so this is actually called a spring pendulum, but it has very similar characteristics to the other mass and spring system that we saw on the last page. The difference now is that gravity is also in play here, along with the spring force, to produce a restoring force. But once again, if we take this mass and we stretch it down and release it, it's going to bob up and down depending on the strength of the spring and how much mass there is here. The last topic of this chapter is on driven oscillations and resonance. So what do we mean by driven oscillations? Well, a driven oscillation is basically an oscillation that is forced from some outside force that's making the oscillation or the system move back and forth. So there are two frequencies that are important to keep in mind here. There is the driving frequency, which we'll call F external. That's the frequency of an external periodic force that drives a system by wiggling it, basically, okay? But the system has its own natural frequency, F naught, or F sub 0. This is the oscillation frequency of the system if it is left by itself with no driving frequency present. So up until now, we have been dealing with systems and only talking about the natural frequency of the system. For example, when we talked about the mass spring system, we had a formula for frequency. That's the natural frequency of the mass spring system. When we talked about the pendulum, we talked about the natural frequency of the pendulum. But now we're going to add something else. We're going to allow an external force to come along and make the system oscillate at a different frequency. So this is what's meant by a driven oscillation. So to make this very clear, here's some examples that are pretty common. When you push someone on a swing like this, okay, the person here is the driving force that's going to be pushing the child at some frequency, okay? And we'll talk about resonance soon. When a diver here jumps up and down on the springboard here, all right, that's the driving frequency. An earthquake has its own frequency as it shakes through the ground. And when an earthquake shakes a building, for example, the earthquake is producing the driving frequency up here. When you drive your car over a bumpy road, the bumps in the road are causing your car to shake or vibrate. And that is a vibrating frequency caused by the road and, of course, the speed that you're driving by. Sound waves that hit your eardrum. When you listen to music, different sound waves have different frequencies. And those different sound wave frequencies are making your eardrum vibrate at that particular frequency. Okay, so let's now take a look at the response curve of a system to different driving frequencies. So when you drive a system by wiggling it at some frequency, the system will oscillate at the driving frequency. However, the amplitude of the driven oscillations depends on the frequency. So take a look at this graph here. This is showing the amplitude, meaning how much the system actually oscillates, right? The distance that it oscillates. And we're going to plot this versus the driving frequency, F external, down here in hertz. All right, now the system has a natural frequency of 2 hertz in this example. All right, so F naught is 2 hertz. This would be the frequency of the system if it was just by itself and bouncing back and forth. But now what we're going to do is we're going to drive the system externally by pushing the system at 1 hertz. And you can see that the amplitude is very small. But look what happens as we approach the natural frequency of the system. As we get to 2 hertz, we reach a peak. And this is called resonance. All right, our driving frequency is resonating with the system here at the correct system frequency, which produces the maximum response of the system. We get the highest amplitude right here when we match our driving frequency to the system's natural frequency. Once we go past that frequency, though, you can see the amplitude of oscillations starts to die back down. So this phenomenon that we just saw on the last slide is called resonance. Resonance is the condition when a vibration's amplitude grows very large due to an external influence that has the same frequency as the vibration. So one example that makes this very clear is to think about how do you push a child on the swing. So the swing has a natural frequency that it wants to swing back and forth. And you can see here that the swing is just a pendulum, right? Here's the mass of the pendulum here, which is the child, and the rope or the cable or the chain that the swing is attached to, that this is the length of the pendulum. So remember the pendulum has a frequency which is determined by this length here. So this swing wants to swing back and forth at a certain frequency. So how does the mom here push the child to make it swing faster and higher? Well, she pushes at the exact same frequency as the swing. In other words, every time the swing comes over here, she gives the child a little push back in the other direction. And if she keeps doing this, the child starts to swing higher and higher and higher because there is resonance involved here, right? The mother's frequency is matching the natural frequency of the swing, and this is called resonance. If the mom here pushes at any other frequency, if she pushes too often or not often enough, the child's amplitude here will diminish and the child will end up just not swinging at all. So let's look at a resonance simulation tool, and we can look at this with a little bit different system. This is a simulation tool that is useful to simulate the phenomena of resonance. And the way it works here is they've got this system down here called a driver. And the driver has a piston here that's going to move up and down, and we can set the frequency at which it moves up and down. And then you can see there's a spring attached to that, and on top of the spring is a mass, this blue block. So what I'm going to do here is start this thing oscillating just really slowly at first. We'll set it to about 0.2 hertz. Let's get this thing going here. Here it goes. Okay, so you can see this thing going down at, up and down at 0.2 hertz. So it's taking about 5 seconds to go up and down once. And you can see that the mass up here is moving up and down with the driver here. Okay, now notice over here the resonator, that's the spring and the mass. It has a calculator in there that calculates the natural frequency, and the natural frequency is set so that it's 1 hertz, 1 cycle per second. But notice we're not matching that. We're only at 0.2 hertz or 0.2 cycles per second. So as a result, we don't have any resonance right here. Now let's watch what happens as I start to increase our frequency here. Let's go up to this is about 0.5, and you can see now this thing is still, it's moving basically with the driver here, but watch what happens as we start going closer and closer to 1. Now we're starting to see the mass up here is actually moving with more amplitude than the driver is here. And as we get closer and closer to the natural frequency, we reach resonance. So look what happens as I get to 1 hertz down here. We've got, this is resonance now. So notice the mass is just going crazy right now, right? The amplitude is increasing every time it pushes it. It increases it more and more. Now as I go past 1 hertz, all right, now I'm not matched to the resonant frequency anymore. You'll see the amplitude of oscillation starts to decrease. And that continues as I go up. I can go, I'm at 2 hertz now. You can see how fast this thing is moving. But notice this, this mass up here has very little response to it. All right, and I can keep going up in frequency. Here I'm going really fast, and notice the mass is basically almost not moving at all. So the key idea, remember, with resonance is we want the driving frequency, the pushing frequency, to match the natural frequency of this spring and mass, and it's set to 1 hertz. So I have to slow this thing back down, and let's go back down. I'll crank this thing back down till we get to 1 hertz, and now watch the amplitude start to increase as I get to 1 hertz. Right about here, we're at resonance again. And so now the mass really has a large amplitude. And then, of course, if I decrease the frequency, we're not at resonance anymore, and now you're going to see the amplitude starts to decrease. Resonance is a fascinating phenomenon in physics, and there are lots of examples of resonance. Some of you have maybe experienced this. It's kind of fun. If you take a wine glass and you dip your finger in water and rub the top of the glass, you can get the wine glass to actually sing. And what's happening there is the vibrations of your finger rubbing on the rim of the glass. They get to resonance with the glass natural frequency. And when this happens, the amplitude of vibrations builds up until the glass actually vibrates so much that it produces sound. But you have to use the right amount of pressure with your finger and the right speed of your finger to produce the right frequency, that is the right driving frequency, to match the wine glass's natural frequency. And you can take this to an extreme by actually getting a wine glass to shatter from just sound. And you'll watch a kind of a very entertaining and fun video of this shortly. Sometimes you may have heard windows in your house rattle when you're listening to loud music, or maybe the TV is playing some music or something, and sometimes you'll hear something in the house, like something on a shelf or maybe a window, will all of a sudden rattle. Well, what's happened there is you've reached resonance. The natural frequency of the window is matched by the driving frequency of the sound, and only certain sounds will cause that resonance. The same thing for those annoying vibrations that you sometimes hear in your car. You might have something on your on the dashboard of your car, or maybe your glove compartment door or something will sometimes vibrate and you'll hear it buzzing when you drive your car at certain speeds. This is because the vibration resonance matches the vibration of the road or the car, basically comes to match the natural vibration frequency of the object that is vibrating, and we get resonance there. Many years ago, the military learned that the hard way, basically, that if they had soldiers marching in step over a bridge, and if the frequency of their steps just so happened to match the resonant or natural frequency of the bridge would start to vibrate. And it can actually vibrate to the point where the bridge can break, which would be horrible, right? So what they would typically do is have the soldiers break their lockstep and just walk casually on the bridge so as not to create a resonant situation. You may have noticed this back, on our campus and the pedestrian bridge that goes to the parking structure. Sometimes when you walk across that, you can feel the bridge shaking up and down a little bit, and that is due to resonance of the people on the bridge walking over it. Taking this to an extreme, there's a famous or maybe infamous example of the Tacoma Narrows Bridge disaster, where wind caused vibrations that matched the resonant frequency of the bridge, and the result was catastrophic. So you'll watch a short video clip of that very soon. Lots of other important examples of resonance. For example, the whole idea of musical instruments is based on acoustic resonance, and this is something that we're going to explore in the next couple of chapters. Lasers, if you think of a laser pointer or an industrial laser that cuts metal, the whole idea of a laser is based on optical resonance. A radio, including the radios in your smartphone, your telephone, your cell phone is basically a radio receiver and transmitter, relies on the phenomenon of electrical resonance. So the last thing we're going to do here is watch a couple of fun videos. I think you'll enjoy these. They show some of the very fascinating effects of resonance. And after that, I will see you in chapter 15. Goodbye.
Yes! All right. Yes! Glass number 90. Yow! And that's proof that it's not a trick. That was too easy, man. Number 93. That's 5 today.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.